We're going to talk about how to write rules for patterns. And you've been working with tile patterns for a while now. So if you look at problem 18 in chapter 3 of Algebra Connections, they have you look at this tile pattern called the big C's. And if you look at this, you will notice that each time two tiles are added here, here, and then two are added there. And then there's two, and 2 each time. So essentially what's happening is you are adding 6 each time. So if that is the case, then that means that figure 0 would not have these, not have these, and not have 2 of these. So essentially it will just have 3 tiles. It's important to do figure 0, even though that doesn't seem to make sense. There's a reason why, and I'll show you why in a minute. But first thing to do is kind of look at, okay, how many tiles are getting added each time? So now that we've kind of taken a look at the pattern and we've noticed that 6 tiles get added each time, it is very helpful to make a table between the figure numbers and the tiles, because then what that does is that allows us to look for patterns across the table and then up and down in the table to see how we could write a rule for what do you do with the figure number to get the number of tiles. And so that is how you want to attack these rules. You want to ask yourself, what can I do with the figure number to get the number of tiles? Well, the first thing we noticed in this tile pattern is that it is going up by 6 every time. It is going up by 6 because we said that 2 tiles got added top, bottom, and in the middle. And we also said that figure 0 had 3 tiles. So if it's going up by 6 every time, then that means figure 4 should have 27. And in problem number 18, they asked you to draw that. So that should indeed be the case, and I'm not going to worry about drawing it here because I want to focus on the rule. So we're adding 6 every time, and the shortcut to adding 6 over and over and over again is to multiply. So in the rule, that's going to look like 6x. But notice how figure 0 started with 3. So 3 is our starting point. So it's kind of like going to look like, excuse me a second, I'm going to erase this and write it this way. We're starting with 3 and we're adding 6 tiles every time. So it's going to be 3 plus 6x. Now in order of operations, we know that the 6x is first. So if you prefer, you may want to write this rule as 6x plus 3. So let's test this. So for figure 4, if I take 6 times 4 and add 3, do I get 27? I do. For figure 3, if I take 6 times 3 and add 3, do I get 21? Yes, I do. So this is a way that you can figure out the pattern geometrically using the tiles up here, and then using algebra to represent how that pattern grows. So it starts at 3 and it adds it adds 6 every time. The second thing they'll ask you to do is make a pattern, a rule for a pattern that is just written in a table. So we don't have tiles this time. But keep in mind that our rule in the last problem had something times x. So we had a number times x, and then we had something getting added. So ask yourself, okay, if I take 2 times something and add something, I get 5. If I take 10 times something and add something, I get 21. 6 times something. So to make that consistent, how would that work? Well, if I look at the 10 and 21, I know that 10 times 2 plus 1 is 21. So let me test that with the 2 and the 5. So if I do the 2 and the 5, 2 times 2 plus 1 is 5. Okay, I want to test it with one more set. So let's do this 6 and 13. 6 times 2 plus 1 is 13. So that tells me my rule is 2 times x plus 1. So then let's use that to help us fill in the rest of the table. So let me clean my board here. So that means to get the value under 7, I'm going to do 7 times 2 plus 1. So that's 14 plus 1, so that's 15. I'm going to do negative 3 times 2 plus 1. Negative 3 times 2 is negative 6, plus positive 1 is negative 5. Negative 5. Let me jump over here to the negative 10. So I have negative 10 times 2 plus 1. Negative 20 plus 1 is negative 19. Then I have 100 times 2 plus 1, and 100 times 2 is 200, plus 1 is 201. Okay. Now I left this one with the negative 15 blank on purpose because we kind of have to work that one backwards. So we need 2 times, oh, I'm sorry. So we need 2 times x plus 1 to equal negative 15, because negative 15, as you guys like to say, is the answer. So now basically I can just solve this backwards. So if I subtract 1, I know that 2x is negative 15 minus 1 is negative 16. Divide that by 2, and I get negative 8. So, does negative 8 times 2 plus 1 equal negative 15? Yes, it does. Negative 8 times 2 is negative 16, plus 1 is negative 15. So that is how you can use a table. Now I'm going to show you a little bit of a shortcut for this one. And so if you're having trouble finding the rule, there is a way that you can kind of do a backdoor approach. And we're going to look at that next. So what I'm doing here on this slide is I'm talking to you about some of the concepts that will connect to things later and also give you a different way of looking at writing the rule and how to find the rules from these tables. So what I did was I took the x values of the table and I wrote them from least to greatest going across the top, and then of course I made sure that the y values were in the places that they should be. Now we do know that this negative 15 is going to go here because we already know that that was negative 8. So we already knew that. But that's why I put that there. But when in doubt, you can always just kind of stick it at the end and worry about it later. But what's most important is you want to look at, whenever you have 2 points that are kind of, and these are points, by the way. I kind of slipped there and called them points, but if you were to graph this, this would be the 0.25 and the 0.613. So you want 2 sets of values. And the closer together they are, the better, although I could use the 6 and 10 if I wanted to, but I'm just going to use these because they're right next to each other in the table. So I want you to notice how the difference between the 2 and the 6 and the difference between the 5 and the 13. So to go from 2 to 6, I am adding 4. To go to 5 and 13, I am adding 8. So think of this as a rate. So for every 4 that I'm going across in the x, I'm going up 8 in the y value. And this becomes an algebra concept called slope, which is the change in y over the change in x. And we use these triangles. These are actually Greek letter delta. And this is showing the change in y, which is 8, over the change in x, which is 4. And this is showing a rate. So the 8 is going up for every 4. So if I were to make that into a unit rate, if you will, I would say that the y values go up 2 for every 1 of the x value. And notice how that was my number times x. So that is where that number comes from if you're just looking at the table. It is your difference in the y's over your difference in the x's. And so that is where that 2 comes from. It's really nice if you have the number for the one below it, which we do for the 7 and the 5, so you can really see it here. So here's your 1, and here's your 2. So it goes up by 2 every time, and since it goes up by 2 every time, that's why it's 2x. And the value that got added in this case was 1. In a table, that is going to show up. That is going to show up as, why won't it let me erase that? As the 0 value. So if I were to extend this table and put a 0 here. So let me even back that up. Let me put a 1 and then put a 0. So this would be 3 and this would be 1 because of the fact that it's going up by 2 every time. So this 0, 1 is where the 1 comes from, because remember that's the starting value. Now, I just said a lot, so I probably confused you. So I'm going to show you another example on the next slide. Okay, so let's take a look at this example. This is a pattern that I just made up, and so I put it in a table and I put the numbers somewhat in order from least to greatest on the X row, and I filled in 3 Y values for you. And that kind of shows too that when we get to graphing lines, you will always want to graph at least 3 points. Even though you only need 2 to make a line, I like having the third one just kind of as a check. So let's take a look at this table. So we notice we're only going up by 1 here, and we're going up by 3 here. So if this were a tile pattern, that would tell us that we are adding 3 tiles every time. And this is a 1 up here, so our ratio is 3 over 1, which is already a unit rate, so we know this has to be 3x. So if it's 3x, where did it start? Well, the good part is the 0 is already here. We know it starts at 2. So if you use just that approach, it gives you your rule of 3x plus 2. So let's use this other point to see if that actually works. So if I have the point 10, 32, and let's say the question might say, is this point on the line, or does this point satisfy the rule? Well, let's take a look. So let's take 3 times 10 plus 2 and see if that gives us 32. And these are x and y, so technically your rule is y equals 3x plus 2. So 3 times 10 is 30, plus 2 is indeed 32. So that point satisfies the rule, and that means that that point on a graph would lie on that line. Even if your graph doesn't go up that far, you already know, just by doing this math, that that point is going to be on the line if you were to zoom out. So then let's use this rule to help us fill in the rest of our table. So 3 times 5 plus 2. 3 times 5 is 15, plus 2 is 17. 3 times -1 plus 2 is -3 plus 2, which is -1. 3 times -3 plus 2, 3 times -3 is -9, plus 2 is -7. So what we've done in this screencast is talk about how to develop rules from tile patterns and from charts. And then later we'll talk about how to graph them and how the graph represents the table, which represents the equation, and how the equation, all those 3 are mixed, and those are called the multiple representations. Thank you for your time.